Good afternoon and welcome to this very first National Centre for Research Methods webinar, which is going to be given by myself, David Martin. We've been talking about automated zone design in practice. I'm just going to explain for you the way in which we're going to operate this webinar. You should find that you're logged into GoToWebinar, and over on the right hand side of your screen is a little control panel which slides in and out, and if you can't see it, there's a little orange slider, a bit like that I'm showing, which gives you, probably the most important thing for you is to understand that your microphones are muted while I'm giving the presentation, but that at any time you can type questions into the question box and we will see them here on this screen. What I'm going to do in a moment is switch on my camera so that you can see that I'm here, and after I've introduced the webinar and told you around about what we're going to be covering, I will switch off my camera and show you the slide set. But as we're going along, you're very welcome to ask questions either specific about what's being talked about or general issues that you'd like to be picked up at the end. And after the main presentation block, I'll endeavour to group any questions that people have put in. Thank you for your hello and welcome messages that I'm already beginning to see. And I'll try and group those together and address things that are interesting to people at the end. And I should also say that at the very end, when we close the webinar, there will be a brief survey, and if you'd be willing to answer the couple of questions that are in there to give us some feedback about how this is going, that would be just great. So I'm just going to switch on my webcam so you can see, hopefully I'm sitting here in Southampton in the offices of the National Centre for Research Methods, and this is the first of a series of webinars, so it's a foray into a different mode of delivery for NCRM. And we've chosen as a start topic this one of automated zone design because it's something which I have a very long history in working in, and which we're aware of quite a few groups in the UK and internationally who have been using the AZTool that myself and Southampton colleagues have developed and have sent in emails, asked questions as people have started using it. And what I'm going to aim to do is to give you a really brief overview of the principles of what we're trying to do and try and address some of the practicalities about using automated zone design in your own research or application setting. We have a couple of little poll questions in a minute which will appear on your screen. Just trying to understand, those of you who are there, there's about 20 of you out there at the moment. I'd like to know whether or not you are already users of AZTool, because that will help me to direct my comments in a way that's most helpful to you, and also whether you've looked at the resources that are already on the NCRM website around this topic. And then if I know that about yourselves, that will really help me to pitch this in a way that's most helpful to you. So in a moment you should see that poll on your screen, and I'll disappear from the live video. Now you know I'm here, and I'll proceed with the slide set when we've done that. So we'll switch to the poll. Do feel free to answer that question. So that's great. So I can see the answers coming in here. So it looks as if about 1/3 of those of you participating have had a look at the NCRM resource, and we have a second question in there as well. It would be great if we could move on to that as well. So it looks like I've got about 1/3 of the people who've used AZTool previously. And just seeing who's made use of the online resources. Okay, so that's patterns reversed, maybe slightly more than half of you, about half to slightly more than half have actually looked at the online material that's there. That's really helpful. That just gives me a little insight into the group of you that are there. So what I'm now going to do is to give you a brief overview of the way in which we conceptualise zone design and automated zone design, and then go and pick off some of the real practicalities, if you like, the nitty-gritty questions which come up every time people try and use this in practice. I'm going to step through some of the, sort of an overview, a quick tour through what happens using AZTool, and I'll tell you a little bit about the research that we're working on in Southampton and within NCRM on various aspects of zone design research right now, but that's quite a small sliver at the end, and I will endeavour to pick up questions if you want to type them as you go. I'll see them on the screen, and if you like to save some of them to the end, I'll try and group them. But if you think of something, put it in, just type it in the box. So I asked which of you have used these resources and whether you've used AZTool before, and that's just a reminder to me to let you know that some key URLs where you can find things like this, where you can find AZTool, are in the slide pack right at the end. So we'll make sure that any of these things that we might be talking about you're not familiar with, you can see them when we get there. Let's take a very brief overview of zone design. Myself and colleagues in Southampton have been working for about 20 years on zoning problems of one form or another. And the main application, the thing they have in common, is that we're seeking to make some kind of optimal division of geographical space. Usually that would be in terms of defining the polygons that could become the areas on a map. That might be for presenting statistics. In recent terms, we have certainly seen people interested in using these tools for political districting, which is an obvious application. Thinking about how perhaps to organise a survey where people are going to be sent out into the field and visiting addresses, and there's a need to balance workload, and some rather more interesting situations where zone tools are being used to standardise statistical results that have already been obtained from medical or administrative data, and even for applications where there's some kind of service delivery area and we're actually planning field operations for something which is extensive over a big geographic space. So the thing they have in common is we want to divide geographic space in some optimal way where we've got some means of defining criteria about what optimality might mean. And the result is usually going to be a tessellation of polygons. There's a long list on my slide here. I'm not going to read them all through, but quite a few of those are areas or area types which are commonly zoned or rezoned. Things particularly like local authority, geographies, those arising from censuses, we often have a need to redistrict them, so they may exist for the period from one census to the next, and then they have to be redesigned again. And as you'll discover, if you're not already familiar, a lot of the original work that I was being involved in with this actually started with UK census output areas. So those are the zones. The kind of parameters of the zone design, which might lead to very different outcomes, might include some of these. Certainly we could choose the number and configuration of those zones. We could think about where exactly we want boundaries to be aligned on a map, and in practical applications that might come down to issues such as how are they aligned relative to the centres of roads? Do they go behind buildings? Have they got to follow local authority boundaries or some kind of official districts that are already in place? Often people that we have spoken to who are involved in genuine zone design scenarios find that they inherit a process which has been done in the past, often as a paper exercise. And it may be that that's been a very carefully documented process because there's been something written down, a team of people have followed rules. But I should say that it's equally common for people to discover that actually there is quite an arbitrary process which has been at work, where maybe there's been some historical rule of thumb for how areas are drawn on the map that's become digitized, and now there's a desire to build a geography which is perhaps evened out so that all the zones have got the same population size or the same number of voters in them, and we're starting from something that's quite hard to understand and document. And so one of my very first pointers in this practical consideration is it's really crucial to be able to write down effectively what are the design objectives, what exactly are we trying to achieve, because that's key to driving any kind of automated process for the zone design, such as we'll be talking about. Sometimes we've got combinations of historical and administrative things, and algorithm has been applied in some way, and different software tools are around which people have used. So the most obvious applications, publication of statistical results, but really quite a wide set. My one example, and I'm not talking about this extensively this afternoon, is the 2001 census output areas in England and Wales. And the reason I use that example is it was the first large-scale use of the work that I'd been involved in. The Office for National Statistics wanted to create a national coverage of small areas that as far as possible were built up from unit postcodes, and we'll talk about building blocks and their significance in a few minutes' time. They had a target size in mind, so they knew that they'd like all these areas to have about 125 households in them, but they really wanted, from a confidentiality point of view, every zone to have more than 100 people and more than 40 households. So already we've got multiple constraints related to population size. And then because these are zones which people were going to place on a map, conduct statistical analysis from, they also wanted some control over the shape. They wanted these to look attractive, compact areas on the map, and they wanted to take into account social homogeneity. In other words, they'd like the same kinds of neighbourhoods grouped together. So already in the middle of that slide, we've got quite a few design objectives of quite different character, all of which are to be brought together in creating a new set of small areas. And the goal in this case was the publication of the census statistics. This map from the very useful DataShine website, which you can see credited up in the top left there, is just one instance from the 2011 England-Wales census of data mapped onto those output areas for central London. And so the work I just described was done in 2011. It was updated and what we've got here is a set of census data mapped onto those small areas, and across the whole country there's a boundary set with 170,000 or so of those zones. So this is a very extensive zoning exercise which is then used as the basis for lots of other applications. There are quite a range of reasons why the way that we place those boundaries matters, and the implications obviously vary according to the application you have in mind. In my census context, it's going to affect the statistics which we report. In an electoral context, obviously it's going to affect the voting results, and it's been long understood, I'm sure you'll be familiar with the concept of gerrymandering, which is literally to redraw the boundaries so as to produce the desired outcome in a result. If we happen to know that all of the supporters of one particular political party are concentrated in certain kinds of neighbourhood, we could redraw those boundaries theoretically so that all their votes are concentrated and they only elect a single representative, and maybe the votes from an opposing party are dispersed into a set of areas where they're just going to win, and they may return more representatives even though their share of the total vote is less. So it's been well understood that the placement of the boundaries allows us to alter those statistical results. But in different applications, the sorts of things that we've been talking to people about recently, the equivalent would be that we could redraw these boundaries, and the result may be that you could give much more work to one surveyor who's going out in the field to knock on doors and collect survey forms than another, and usually the objective is to equalise some characteristic, population, voters, workload across the entire area of the map, and that's really the task we're about here. Statistically, the geographers among you will be familiar with what we call the modifiable aerial unit problem, which is the well-known effect that as we change the zone boundaries, we change the observed statistical relationships in the aggregate data. So we may have a relationship between unemployment and poor health, and if we redraw the boundaries on the map, we will actually change the detailed relationship. And again, in most applications here, the goal is to try and produce as neutral as possible a set of small area units. So many reasons why, lots of different applications, it matters which set of geographical boundaries we use. There's much more detail about some of that and illustrations of how the zone design's been used in the online resources I mentioned. What I want to do now is to turn to think about how does it work in practice, and what might we do if you are a user or a researcher with a specific need to create a new set of aerial units. So here are the principles. We want to achieve a set of zones that meet specific design criteria. Maybe they're not too big, not too small, sensible shapes, similar populations. And we have to recognise from the very start that any solution that we come up with is going to be a trade-off between competing objectives. We cannot, for example, take any settlement pattern and divide up so that all the zones have got the same population in the same area, because generally speaking human population is very concentrated in urban areas. If we make all the populations the same size in the rural areas, the zones will be geographically much larger. If we make all the zones the same geographical size, then the ones in the urban areas are going to have higher populations. It's a trade-off. And this fact that what we're doing in any design situation is to try and formalize that trade-off is exactly what we're about with the use of automated zone design tools. It's being able to write down and formalize the type of trade-off which we want to achieve, and then use the software to help us reach something which approaches the best possible trade-off. The natural human way of thinking about subdividing a map, the one that probably we would all try if we gave you this as a paper exercise, would be to take the entire area and start drawing lines on the map in order to subdivide it. But actually the computational approach, which most algorithms for solving this kind of problem follow, including our own tool, which I'll be talking about, is actually to consider what are the smallest building blocks that we could actually put together. You could think of them as the jigsaw pieces, and then to look at what happens when we put the jigsaw pieces together in different ways. So computationally, we're building from the bottom upwards rather than from the entire population and splitting downwards. And that is a key principle for all of the generic approaches which I'm talking about here. Now, very specifically, we have a tool called AZTool. Again, the URL follows later. And the language that I'll use for the remainder of this presentation is that we seek to take those small building blocks and build them up into tracts. And that language means that I fall sort of free from any particular application to do with survey design or network allocation or censuses. We're taking building blocks and we want to build them into tracts in some way that meets the design criteria that have been set out. And computationally, this is a highly iterative process whereby we're going to make an initial assemblage of those building blocks in some way which is, if you like, a first approximation to the constraints we set, and then we make many small changes, seeing whether each small change is an improvement or not on the solution that we started with. And our goal is to keep doing that until we get some kind of best solution. And I'm using best here in inverted commas because obviously we could keep going and find that just one more iteration would have produced something slightly better. And so the practical consideration here is that for any problem space we're working in, we tend to run this, restart the problem from different initial random aggregations, let it run many thousand iterations, or certainly many hundreds of iterations, and take the best from that set, because we would usually find the types of problems this has been applied to, when we've done that, we're actually not making much more improvement. And understanding the anatomy of your particular application is another important practical consideration. And as we'll see, it's related to various factors, including the relative sizes of the building blocks and the tracts which you want to produce. I just note on this slide that there have been quite a range of software implementations for automated zone design, including Sage, which was around in the early 90s, ZDes, which came from work led by Stan Openshaw and then Seraphim Elvanides at University of Leeds School of Geography, AZM, which was a previous version of my own work in this area, and AZTool, which we're currently using, and I guarantee you will find others. But certainly the ones I've listed here share an origin in some of Stan Openshaw's automated zoning procedure work. So AZTool was developed by myself, colleagues Sam Cockings and Andy Harfoot here in Southampton, and I started this work actually by coding a version of Stan Openshaw's automated zoning procedure, which he'd originally published right back in 1977 with a brilliant idea for how to tackle this problem, but actually with very little computational power and very little digital geographical data available. So although the concept was there, there wasn't really a practical way of using it because nobody had the data necessary to solve a problem of this kind. The version which we're currently using is programmed in a .NET environment. It should run on any modern version of Windows, and it's freely accessible. You can download it and use it. So here in cartoon mode is how AZTool operates. I've already talked about this idea that we might start with a set of building blocks. So I've got here 4 little building blocks for you. These might be, in the census case, perhaps these might be unit postcodes. And what we'd like to do is group them together to produce some larger units which might be suitable for the publication of statistical data. And so the next thing we're going to need is some design constraints. And the design constraints are the rule set. And each time our team has sat down with people who've been thinking about using this, it's really worth investing in thinking this through. Because the design constraints are those things I was just talking about. What size zones are we really aiming at here? What do we want to produce? Is there a minimum allowable threshold size? So we must produce things that have got more than a certain population, less than a certain population. Do we have a particular target size? It may be that we want to produce zones that all nest within some middle-level geographical units to do with local government or administration. But I'll talk a bit about how we can specify those later. But it's essential that we spend time thinking what are the characteristics that would make an optimal outcome for our particular application. The construction of the building blocks I will also return to if that's something that people are wondering about. What AZTool does is to take those 2 sets of information, the original building blocks and the design constraints, and make something that we call the initial random aggregation. And it is just that. You can see in my cartoon mode here, the red is just a combination of 2 of those zones. I've put them together to make 3 zones because I need a starting point. And what AZTool does is to use the information provided to construct this in such a way that those 3 zones are not far away from the design constraints, but they're unlikely to be optimal. The red one may be too big, the green one may be too small. And we then go through a series of iterative recombinations, putting the original building blocks together in different ways and evaluating how good each of these solutions is compared to the best one that we've seen before. And that evaluation will be using different calculations according to the constraints, and I'll say something later also about how they're weighted, but they're weighted relative to one another. When we've done that over a large number of combinations, we would choose a particular set of output tracks which in the constraints given is deemed to be optimal, and that is the fundamental process through which we're working. That's what AZTool does. Now, another thing which we're very frequently asked is about the construction of building blocks. And it depends, again, on the nature of your application. But those building block zones are very, very important because all of the boundaries of the final solution can only contain the boundaries of the building block zones. So in this case, if I'm building from postcodes to census output areas, my output areas will only be aggregations of those postcode building blocks which go in the first case. Now, in some instances it's been possible for people to use pre-existing zones, and in others we've had quite a lot of debate about what is the most appropriate way of building these purpose-built. So in recent conversations we've seen people using maybe some pre-existing zones like local polling districts that may have been available to the organisation. That was a good idea, it fitted in their context. And in others we've needed to actually construct purpose-built building blocks because there was no suitable zone, and they might be something like street blocks, they might be clusters of addresses, a particular version of a postal geography. So this really does depend on the specific application. But what they do need to be is small relative to the intended outputs. My little cartoon version, as you may have just noticed, only had 4 input building blocks and 3 output zones. So actually there's very few permutations. I think there are only the 4 and 3 of them were in the cartoon. The fewer building blocks we've got, the less permutations there are to produce a solution. So that might make the computation very fast, but it's unlikely to produce a very elegant solution, especially if we pile on a lot of constraints. And it is quite possible for over-enthusiastic users to initially pile on too many constraints and find that AZTool just reports an error for them and says, you know, I can't solve that. And again, there's a practical thing to bear in mind. It is quite possible to set up a problem of this kind with too much complexity and then to be unable to find a solution and then have to relax the constraints. So if, for example, you said you wanted to take the whole of southern Britain and divide it into some catchment areas and they must all have more than 450 people and less than 550 people, and you want to build them from census output areas, it won't work. There will not be a solution because some of the output areas themselves will already break that original design constraint. So there's no way it can be done. And actually that requires some thought because it is quite possible to set up problems that can't be solved. If the building blocks are small, we have a lot more degrees of freedom for exploring different solutions. Generally speaking, somebody will be working with a GIS. AZTool itself is not a mapping tool. It's not GIS software, but we've set it up to take the building blocks which somebody may have created in the GIS, run AZTool independently and then re-import. And there are various degrees of interconnection in terms of writing bits of code that start AZTool's runs or which can call it from macros inside other software that we've seen people playing with. But effectively it's a standalone tool, assuming GIS data coming in, GIS data going out. Clearly we're going to need some statistical information which actually allows us to evaluate the design criteria for each building block. So if, for example, standardized population size is the thing you're aiming at, we need to know the population on each building block. So if you go in the GIS and you generate these building block zones, there have to be relevant attributes attached. And whether that makes sense in your particular application is one of the key things to think through. In the census case, it's possible, for example, for the Office for National Statistics to use confidential data at the building block level because that never gets published. And in fact, the goal of the exercise is to combine the building blocks until they get to a size at which the data are available for publication. If you're working on a research project or within a business setting or a local government setting, you likewise may be able to construct building blocks using organisational data which we'd not be able to release in order to help you construct a zonal geography, which might then be used completely separate from those data, serving some other purpose. But just because we use data that we couldn't publish in the construction, it doesn't mean that data has to carry across into the output. Here's a little cartoon, and I'm not stepping through the whole sequence here, but in this particular instance, which is back from the 2001 census geography, we didn't have individual property boundaries, but we did have reference points for every address. So the blue dots are the individual addresses, and in this case, T-SYM polygons have been constructed around them. It's a fairly easy GIS operation, and they've been clipped off to those black boundaries, which were probably something like census enumeration districts at the time. And that's allowed us to create a set of building blocks. We then dissolved away the boundaries between all of the postcodes, all of the addresses that share a common postcode to create these postcode building blocks. That's a perfectly viable way of proceeding. That's actually rather outdated now. If we were starting again, there would be a full digital data set for all the property boundaries in the background. You could construct a set of building blocks which neatly snap to those property outlines, but you'd have to think through whether that was a worthwhile thing to do in terms of the complexity of the data set, number of coordinates that are going into it, the amount of pre-processing that's required. And again, something over the years I've seen more than once is people getting over enthusiastic about creating very, very elegant building blocks. To bear in mind that when you actually run AZTool, only a subset of these boundaries will be carried across into the output tracks, the geography we're going to create. Most of these will be lost because we're going to put a lot of these areas together to make each output area, polling district, service catchment, whatever it may be. But you will find that users don't tend to like the sort of wiggly boundaries we've got on the screen here, and that's for a very good reason, that everybody's now used to seeing very clean GIS boundaries. Particular issues if you're working with urban data is whether you want these boundaries to go down road centre lines and the way in which you might want them to follow around properties, whether the properties that are on a street should be included both sides of the street together and you split through the blocks, or whether what you want is to use the streets as the divisions. And that really, again, is one of those things that once you've made the initial decisions, you're going to have to live with it. It's really worth spending the time thinking about your stakeholders, thinking it through. So those building blocks have a big impact on the design solution. The outputs can't get smoother, they can't be more realistic, they can't be better aligned to the real world features than the blocks that we've actually used. And as the number of building blocks increases, we get more permutations, longer computation times, but probably a more elegant solution because we're building up our outputs from much smaller drivers. It's worth also just remembering, especially if you've not got involved in using this before, that it's the contiguity relationships between the building blocks which are the key drivers of the zone design process. So it's which ones are next to which and therefore can be combined. That's what's going to determine the solution. So you could have the same set of building blocks with really crude looking boundaries on the map. As long as the contiguity is the same, they'll produce the same solution as if they've got beautifully elegant boundaries on the map. But as soon as you change the contiguity relationships by redrawing the boundaries, you will start to get different solutions. I'm going to just make the reminder at that point. I see one or two interesting questions popping up in the background there, so I'm just saying I'm noting that there's that I can see what people are putting in there, and I will perhaps pick up some of those along the way. I won't stop and read the detail of those questions, but I will come back to them all. I've noted them there. So the kind of constraints we've got, obviously we've got some things which you say, well, they must be met. There must be more than 100 people or 40 households. I must not cross a local authority boundary. Those are things which are, if you like, absolute requirements of the viable solution. We also have what we might call soft constraints, which we're unlikely to meet exactly, or almost impossible that they would be met exactly, but they're objectives and we want to get as close as possible. So for example, saying that all the zones should contain 125 households, actually the total population might not be neatly divisible into 125, but that's a target we want to get as close as possible. Likewise with constraints to do with shape. And obviously for those criteria, we're going to need some appropriate kind of measurement. So in that case, if we want our building blocks to have a particular population target attached, we're going to need that population already on there. If we can build building blocks in such a way that they've got a meaningful structure for the task we're wanting to perform, so if for example it's to do with addresses and we're using postcodes, the postcodes have got a kind of a natural relationship with the addresses, and that might make sense. For a different application, it might be that you're interested in work that's to do with the streets or the delivery network, then maybe the street boundaries ought to be part of the building block boundaries. That again might be a consideration. Other things we might want to solve for, it may be that we're doing a nested problem. So in this case we may say I'd like to work across the whole of the region, but I want all the output areas I create for the City of Southampton to fall inside the City of Southampton boundary, and then I'd like all of the ones that go in the neighbouring area of Winchester to fall within the Winchester boundary. That would be solving within a given region. That's a very familiar kind of scenario which is often encountered, and most of the census applications which we've used have that kind of constraint in them. The statistics where we're approaching a target, we have often used sum squared difference. So for example, if 125 households was the target, we may actually say what we want to do is minimise across the whole problem the squared difference between that target and the populations we've actually achieved, or for example minimising the sum of perimeter squared over an area. So we're using their statistics which can be calculated at every recombination and allow us to test how we're doing relative to that target set of criteria that we set. So not going through looping all of these, but in the little example I just showed you, it may be that the final result looked a bit like this. 3 of those polygons, building blocks, got put together to make this yellow area. 3 others down here got put together to make that green area, and these on the left got put together with the blue. The advice in general is don't apply too many constraints because they're all competing with one another. So there's really a challenge here to prioritize the constraints that really matter for the application you have in mind, to use building blocks which have got a natural relationship with the problem you're trying to solve. So for example, which makes more sense, addresses, postcodes, things built around streets, which one will actually take you further towards your solution, and then not try and add nice to have constraints that may actually detract somewhat from your ability to achieve 2 or 3 really important ones. If you're looking for instances where these have been used, I just kept that slide in from a previous slide pack I've used. Just these are areas in which automated zone design using our tools are already in place. So 2001 census output areas, lower layer super output areas from 2004, the 2011 census geographies, output areas, super output areas, and the new geography of workplace zones, Northern Ireland output areas and small areas for 2001 and 11, and the newest of them is the workplace zones for Scotland, Northern Ireland, to add to the England and Wales set. So the Office for National Statistics and the NISRA and NRS have used this approach for those standard zonations, which means that if you're looking at them, you will be able to see, if you like, that they are a result of the process which we've just been describing. What's also very interesting is that increasingly we're able, and it's great to be able to do this, to look in the literature and find people who are citing the use of the AZTool in order to tackle particular research applications. So this particular paper is just from a couple of months ago, and it's actually a Danish study which was interested in looking at relationships between mental health and migration, in fact, and the challenge that they had was that they got data for small areas. In this case they were parishes, and the parishes they got, some of them vary very widely in size, and they weren't appropriate denominators for the kind of population health analysis which the researchers wanted to conduct. So what they did was to use AZTool and actually put in those parishes, they got very small ones, and then allowed some of them to be collapsed together to make larger zones, thereby reducing the variation in the boundary set. So there's a very different application where we have no particular involvement, where somebody's picked up the tool and is using it for a very specific need to standardize across a set of small areas. That one at this moment, I'm citing it here, and I'd love to look in and learn more about it. But it's a very different example, but where precisely the same kind of considerations have been put appropriately in place and used by this research team. So the third thing I want to just concentrate here on is, what does it look like when you use AZTool if you go ahead with a problem of that kind? Firstly, to say this is the page from which you can download AZTool. The URL is up there, but it's on the final slides in this presentation as well. There are 2 pieces of software that you'll get from that page, AZTool itself, and there's actually an AZTool importer which will bring in a shapefile from GIS, and there's some README files and other useful material on that page, including an email address that you can contact us on. And if you do download AZTool from there, you'll find it's a zip folder which contains the software application, some user notes and some sample data, and that sample data allows you to understand what's going on with a very simplified data set. Our expectation is that what you'd be likely to do is to get that running and understand it, and then think about how you'd want to adapt the instructions used here to apply to the specific data set that you may be wanting to use. The inputs that are required are a pair of, well, effectively for your set of building blocks, a pair of files which are, we refer to as .aat and .pat files. For those who've been working with GIS for a while, you may recall that those used to be standard file formats used by Esri's ArcGIS software. Although ArcGIS does not any longer use that file structure. They're very simple text readable files that give us the necessary information for doing this task. The AAT file contains the ARC attributes in Esri's terms, that is effectively the characteristics of the boundaries between the building blocks which are contiguous. So in other words, if we've got zone 1 is next to zone 2, it describes the boundary saying zone 1 is next to zone 2, how long is the boundary? Maybe zone 1 is not next to zone 3, there won't be an entry for it in that file, and therefore there's enough information in here for us to reconstruct the contiguity matrix and know which building blocks can be combined with which. The coordinates aren't needed. We'd have them in the GIS. You could export them as a shapefile. If you've got your own software that you could write these files directly, that would be fine as well, but we need these two sets of information. And we're also going to need in the PAT file, these are the polygon attributes, the information such as the populations, maybe this social housing data, might be the geographic unit areas, any constraint that you want to build into the process goes in the polygon attribute file. So in the cartoon version that's downloaded with the software, you'll see you read in the data from the shapefile, it looks like this. It's a very simple configuration with these zones in there. And the reason for doing this is that the very simple example allows us to step through, and for you, if you're using the software for the first time, to really pick through almost an example you could do by hand and understand exactly what's going on. So these are the two data files which produce that map. On the left is the ARC attribute table, and on the right is the polygon attribute table. So what we have here is 3 columns, and these relate to the boundaries between the polygons. So this very first row at the top of the ARC attribute table is the boundary between polygon 0 and polygon 1, and it is 100 units long. This next row is the boundary between polygon 0 and polygon 3. It's also 100 units long. In the map I showed you, which we'll just go back to it, the outside world over here is actually, in this particular instance, is actually labelled as polygon 10. And so the outside of this map is also written in there. Polygon 7, polygon 10, has a length of 300 units. That's actually this light green one in the corner. This is polygon 7. The outside is polygon 10. 100, 200, 300 units is the length of the boundary between them. Over in the polygon attribute table, we've got some characteristics for each of those zones, and the precise columns that are present in this file can vary somewhat with the application that we're using. In this one, we've got the identifier of the zone, its area, perimeter, some data related to homogeneity characteristics, another identifier in there, a population, and some tenure data, as it might be imaginary census data. And actually the 5th column in here is the one which has got the populations on the zones. The last one has got the areas which we're going to use for this. And zone 10, the outside, has got a dummy record full of zeros with a -1 on the end. It's just known to be the outside. We're not going to use it. So those two input files constrain everything that we need to know. We've got the populations. We could specify information about a region. There's no region set in here, but if it was subdivided, so we've got some kind of county level that we needed to constrain, we'd have that in that polygon attribute table as well. And although I'm not talking in detail about homogeneity here, if we have a variable which, for example, is split into a set of types, and that might be the proportion of households living in public housing, the proportion of households living in rented housing, proportion of households privately owning their accommodation. We could put those 3 variables in also and then use that group of variables to control for homogeneity. So in that instance we need several variables because they come together as a homogeneity set describing the split of tenure across the zones, whereas population is just a single value and we can make more than one calculation. If you're working from ArcGIS or indeed any other QGIS, any GIS software that's got shapefile, it create a shapefile for you from your building blocks, then the second little tool that you can download from that page is a shapefile converter. You put in the shapefile, it writes out the AAT file for you, so you can actually get the contiguity matrix information. You don't have to construct it for yourself. So if we now look at our map in the GIS, we would see that these are the attributes. This is exactly the table that we were just looking at attached to that map. So here we are with the same data relating to each of these zones. There's polygon 7 with its perimeter and its population of 75 sitting down in this corner. And if I were to map the populations, those are actually the populations in this demonstration data set. So you can see we've got some higher density zones up here. This is a shaded map by density, or actually a shaded map by count, which I wouldn't normally recommend my students to do, but it's there for a purpose. These are the zones with 100 people. We've basically got a more densely populated area at the top left here, a more sparsely populated area. Actually, the population density may be very similar at the level of the quadrants of this map. There's 100 people here, there's 400 up in that top corner, but the detail distribution differs. And our goal here might be, can we split this up in a way that gives us output areas with, say, as near as we can 300 people in each of the output tracts? That might be our goal. Therefore, that's the way that we're going to set up this run and actually try and operate it. AZTool runs by having a text-readable XML file which contains all the program parameters. And the reason that we've done it this way is that you can set it up for a program run it, and then you've got a saved version of the exact instructions which were used. You could pick it up, you could edit it with the text editor, make some small adjustments if that were necessary, and then run another scenario, save it to a different name. And therefore there's a straightforward way of keeping an exact record of the input commands which are used to produce a separate output. And that mode of working makes sense because AZTool is, I hate to disappoint you if you're not a user, it's no fun to watch, because effectively it's just doing a lot of swapping. This is not a GIS operation, it's not animated. We're really just wanting to get the most efficient possible swapping. So we use the XML file to contain all the program run parameters. You can run it from that command line, or you could even write a batch file in Windows and run a whole series of these and set them going. Go off and have a weekend away or a cup of coffee. This is what's inside one of the XML files. I'm not stepping through all of it here except to say there's a standard structure which the documentation in the download zip file explains the key words here. And we could see that what we've got is the key program options. The input pat file gives us the name of the file. The input arc attribute file gives us the name of the file. It tells us those files have got a header. It tells us some basic information about which column's got the index, whether or not we're using intermediate regions. In this case we're not. And then tells us about how we want to use those variables. And I've got a highlight on the next slide just of this block of the file to give slightly more indication of what's going on. So here I'm just looking at the variables which is to do with the population target. I've got some target threshold variables. This is how they're defined. There's a variable called population. It's the fifth one in the file. It's true because I'm going to set the target. So actually we're going to use it here. I just said I'd like zones with 300 people. So that is my target value. The tolerance, which here is set to a very large value, would leave it set there, is rather more to do with the way in which the initial random aggregation is initially configured, and may interact a little with the complexity of the constraints and the size of the zones. Leave it to a large number. It's not going to interfere for this example. And this has got a weight of 100. Now, weighting in here is an interesting scenario because there isn't any absolute way of giving the weighting which allows you to take something like compactness of shape and express it in the same units as target population. So the way that we work is that you can put a numeric weight in for any constraint you're using, And if those weights are the same, if we gave this a weight of 100 and some other constraint a weight of 100, they'll be given equal weighting as AZTool runs. And what it actually does is it considers that an improvement of maybe 1% in the population target would be the equivalent of an improvement in 1% in the shape target or anything else that we've got set. But the weighting really needs to be worked out for the specific application by experiment, because we can't set an absolute metric that's going to work across all the types of constraint people use. In this particular case, I've got a minimum threshold set, still using population. It might be 100. I don't want any zone to have less than 100, and I've got a maximum threshold set, and it's 625. So you see how in that little block of the XML code we've set up the population constraints which we want to run, and that's taken from the sample file. When the software is running, effectively all that you would do would be to bring in that configuration file and specify an output. And as it runs, it reports some outputs to an output window if you're doing it live and you're watching what's going on. And you'll see that the reporting going through here is what's going on from an initial random aggregation and then a certain amount of swapping that's been going on. And then we start another run, we do some more swaps. You'll get a text format log file which is basically the same as was in that window, and also a CSV format results file which contains what you need if you're going to take it back to the GIS. And normally we would expect that people would take these results and go back to the GIS software from which the building blocks were created, and that would be the place at which the output tracks are first visualized. So on the left, this is the log file, and this is an example of the output. So for the same example we've just been talking about, we've got the ID of each of the building blocks. They're not necessarily in the same order, and the ID of a tract to which they have been allocated. So in this case, zone 7, that was the one in the bottom right hand corner, has been allocated into tract 4 along with these others. So if we take this file, put it back into the GIS where the boundaries were present, and dissolve away on tract ID using a standard dissolve function, we'll get a set of outputs. So in this case, back in the GIS, we've taken that little output file and we have imported it, joined it onto the end of the original data. I'm conscious that I'm talking here, making the assumption people have some GIS facility, but everything we're doing here is very standard functionality in the GIS. So now our original GIS data and the polygons we've got here are augmented with their identity, which tract they belong to. And there in the background, I've got a tract labelled number 7 and a tract labelled number 4. And this is our building block that we keep referring to. It's in number 4. The reason they're numbered 4 and 7 and not 1 and 2 is because in the process of the swapping, quite a few possible outputs may have been created and thrown away, and in this particular scenario it's numbers 4 and 7 that have persevered through right through to the end. If we want to understand whether this solution is any good, clearly we want to know what characteristics it's got. There's the dissolve so that we've got our new boundaries, and these are the populations of those two tracts that have been created. They're both 350, and if you recall, the target we gave it was that we wanted as near to 300 as you could get. There must be more than 100 and there must be less than 625. And when you consider our original permutation, actually this lot sums up to 700, so it's not possible to make an exact division into 300s. 350 is as near as it could get, but our other constraints have been met, and effectively you watch backwards and forwards, the slightly denser patch over here has been grouped and the less dense patch over here broadly has grouped across a bigger area to produce those two tracts with 350 in each. So we could add constraints, higher level regions, we could play with more population targets, we could put a second population variable in, we could put something like households in there and so on and meet both of these. We could play with shape compactness, we could play with inter-area correlation for homogeneity. The latest version of the code, which is not currently on the website, but which we're hoping will be there on the new version of the website, not too far into the future, has got some new features in terms of being able to link zones which are not necessarily absolutely contiguous, but which could be constructed with network connectivity. And effectively that's using a variable which we could construct outside in the GIS and say these two things have a connection, and we would be able to edit effectively the contiguity matrix to give a measure of connectivity which is not just being physically either side of the boundary. Incidentally, people often ask about islands. If you're dealing with a zonation problem and you have an island in there, you can edit the contiguity file and make sure that your island, which might otherwise have no boundaries, is hardwired to have a connection with some other zone in the map, and that would allow, for example, an offshore island to always be connected into the zone solution via the nearest thing on the mainland. Not an uncommon scenario to encounter that. I'm just going to close with a couple of insights into what we're currently doing with the tool, and then I'll very happily, if people have got questions they want to pick up, I'll show you some URLs. You should say again, if you've got questions you want to put in by typing them into GoToWebinar, feel free, but if you'd like to follow up via the email address because you're interested in using the tool, you can do that as well. Several things which are currently going on, both within the National Centre for Research Methods and within Geography and Environment at the University of Southampton, where we've got kind of two overlapping teams interested in zone design. We are interested in further exploration of modifiable aerial unit effects in data, where we can rezone data we're using a synthetic data set here, and we're rezoning to understand some of the implications of standard deprivation indicators and standard geographies, and also to work out how they impact on some of the very common statistical disclosure control measures. So if you do set a population threshold of 100 people and 40 households, how often would it be possible to actually get smaller zones where meeting those same constraints and providing the same degree of disclosure control? This is not work that the Office for National Statistics has signed up to. It's effectively a geographical research to understand the impacts of the disclosure control measures that we've applied on the data which people may be reporting and using, and whether that's got impacts for the analysis they perform. So we've got a set of work going on around that. And we also have a couple of other things which are ongoing and may be presented at some conferences this summer, where there's work going on looking at the possibility for designing new census workload areas and new survey areas which could be applied, if you like, for enumeration design or for survey design, where the characteristics on the building blocks are not just population, but in a sense measures of workload. And what we're seeking to do is even out the workload in a geography which allows us to allocate a workforce. So those are all current strands that we are specifically working on. The disclosure control strand I'll just show a tiny bit more from. Obviously individual data that people are using these days from increasingly from administrative linked records are potentially identifiable, and if location's given away, that's key. It's important to disclosure. And so we've always aggregated over the geographical areas. Everything we've just talked about is an example of that. Usually there's some record swapping, minimum thresholds, collapsing of classes, but those areas, those issues need really, they're being pushed further and harder by the fact that we're increasingly in a world in which researchers are getting data being linked and analysing it in a secure laboratory setting, and then there's a question about what they may be able to take out of those secure settings. And so we're experimenting with the way in which these zone design tools could be used either with a data provider or conceivably in the secure access laboratory to work out what's the most research useful outputs that can be put out while still preserving all the required confidentiality constraints. And this, just as a little sample, is a building block set. These are postcodes in Hampshire, so this is Southampton. If you're, it's great to see folks from really some quite different parts of the world joining in this afternoon. If you don't know our region, we're here in the city of Southampton. This is the sea at the bottom. This is the county within which we're located, and we have here alternative zonations of some of the standard statistical units. This one, it so happens, are the real units. This one is a completely alternative set which we've built because we're wanting to understand the implications of how well we can control population size and whether or not we could build, if you like, more useful zones that meet all the requirements but actually have more stable population characteristics, measures like deprivation and access inside them. So that's just an indication of what we're currently working on. AZTool is available, it's being further developed. We only have a limited team. We tend to work on further developments that are close to our own research interests or close to the team's needs that we're working with. And my practical tip, Dave's practical tip for the afternoon is a lot of the effort here does rightly go into working out the design constraints which you need to use for your particular solution, and in getting those original data set up and testing, because the better the thing is set up, the more satisfactory the results. So that's my kind of headlines from there. I'm going to put one more slide up which has got a couple of useful URLs, and we'll make sure that those are available and that sits there for a while. But what I'm now going to do, if I can manage the webinar technology, is perhaps turn the webcam back on, but I'll also have a look at some of the questions that you've been asking. If you want to jot those URLs down,